Hello, in this video we are going to study about the multiprocessors. A multiprocessor system is an interconnection of two or more CPUs with memory and input-output equipment. They are MIMD systems. MIMD means multiple instruction stream, multiple data stream. So the term processor in multiprocessor can be either a CPU or an IOP. IOP is input-output processor. So a system with a single CPU and one or more IOPs is usually not included in the definition of a multiprocessor system unless the IOPs have computational facilities comparable to a CPU. So IOP must have a power of equivalent to CPU, then it can be considered as a multiprocessor system along with single CPU. The difference between multiprocessor system and the multi-computer system. In multiple computer system, we have multiple computers which may or may not communicate with each other. So in a basic computer network, we have different computers which are interconnected, but it is not having multiple processor. Okay, and if we take a system of multiple processor, it is a system which is controlled by one OS that provides interaction between the processors, and all components of the system cooperate in the solution of a problem. Multiple processor, a single computer will have a single CPU along with maybe IOP with the equivalent power of a CPU, or we have multiple CPUs within the single computer. Alright, so multiple CPUs or multiple IOPs can work together to make a one multiple processor system. Advantages of a multiprocessor system. Multiprocessor system improves the reliability of the system because if in case some part of it is failing, the other parts can work correctly and get the work done. And multiprocessor system results in the reduced loss of efficiency. Obviously, in case of a failure of a single processor, then others can work. A single part of the system cannot affect whole of the system if even one part of the system fails. Multiple independent jobs can be made to operate in parallel, so parallel computing can be done, and even a single job can be partitioned into multiple parallel tasks. Classification of multiprocessors. So they are shared memory multiprocessor, also known as tightly coupled, and also loose coupled multiprocessor, which are distributed memory multiprocessor. So in shared memory, CPUs have their own local memory as well, but there is a common shared memory. But in a distributed memory, all the processors are tied together by a switching scheme designed to route information from one processor to another through a message passing scheme. So messages are passed, and each processor has its own local memory. So in distributed memory, they have multiple memory. Everyone has their own private local memory, but in the shared or the tightly coupled, they have their local memory, but they also have a common shared memory. Interconnection structures. The components that form a multiprocessor system are CPUs, IOPs, and a memory unit that may be partitioned into a number of separate modules. So there are different types of interconnection structures which can be done. So one of them is a time shared common bus, multiport memory, and the other ones are crossbar switch, multi-stage switching network, and hypercube. Let's see all of them. So in a time shared common bus, there is a single memory unit which is being shared by multiple CPUs and IOPs. So different processors, they may be IOP or a CPU, they are all sharing a single memory unit. If single CPU is sending a message, only one unit can send a message to the memory unit or between each other. At one time, only one thing can be done. No multiple communication can be done. So these are the limitations. Enables one transfer at a time, and the overall transfer rate is limited by the speed of a single path. The processors in the system can be kept busy more often through the implementation of two or more independent buses to permit multiple simultaneous bus transfers. In this dual bus structure, so one thing can be noticed is we have local bus and the system bus. So these are two buses which are used, and for each local bus there is a local memory. For every local bus there is a local memory, and CPU IOPs can be used even together, and even a single CPU can work here. So system bus has a common shared memory. So this combination of local bus and system bus is known as dual bus structure. So this is the multiport memory. In this, at these four places, at at the bottom of mm1. So we have 4 lines. These are 4 ports, and these 4 ports are being controlled by this memory module, and based on it, the CPU and memories can connect each other and send messages to each other. The memory access conflicts are resolved by assigning the fixed priorities. So all the ports have their own priorities, and these priorities will dictate what kind of message is being passed and between whom it is being passed, because in this we have different wires connecting each other. So this the advantage is that high transfer rate is there, but the disadvantage is there that we need a expensive memory control logic, and a large number of cable and connector are used, and also it is used with a number of small number of processors. So this system is usable when you have a small number of processors. So the system contains a number of cross points. So this cross point, this combination, this intersection of mm1 and cpu1 is the cross point, and the system consists of a number of cross points. There are multiple cross points placed at intersection between the processor bus and the memory module. So these cross points are responsible for sending the data from one cpu to different memory, or whatever the case may be. All the decisions are being taken by this cross point only. The difference between the multi-port memory and the crossbar switches: multi-port memory has different ports which are being controlled by priority, and the messages are being passed. There may be conflicts, but they can be solved by using the priority method. And in the crossbar switch, this crossbar switch has cross points. This cross point is responsible for handling which data is to be passed where. And the detail of this cross point is here. In this cross point, all the different CPUs are being connected through the multiprocessor. All the data address and control part of the CPU1 or CPU2, all these things are being passed through the multiprocessor and to the memory. So this memory module is, for example, this mm1. So this memory module is being shown here, but only for, let's say, a single memory module is being shown, not the multiple ones. So there is a data bus, address bus, read write commands can be done, and memory enable. So if memory enable is there, then only this memory can act upon. So the multi-stage switching network is, in this we have 2 inputs and 2 outputs. There are 2 inputs, A and B, and 2 outputs are 0 and 1 here. So any input can connect to any output. So A0 A1, B0 B1. So this interchange switch can be operated like this, and it can also be shown like this. So let's say P1 is connected to 1, and this one is again connected here, and this one is passing as 0. So these values in sequence, let's say this 0, this 0, and this 0. So this path, if taken, it is known as 0 0 0, and if the path is taken as 0 1 or this like 0, so 0 1 0 is this. So different 8 memory modules can be handled here using these number of switches. So there are 7 switches being used here, and at different levels the outputs are deciding what kind of value is being decided to be reached. Okay. There is also one more method. It is known as 8 into 8 omega switching method. So in this there are individual paths only. So if we want to go to 0 0 0, so we can go from here. We can reach from this place, and if we connect, let's say 0 1 2 3 is being connected to 0 1 2 3 on the right side, then we can say that 4 5 6 7 will not overlap here, but it will come here only. So this overlapping is avoided, and if upper half is going to upper half, then lower half will go to lower half. In the interconnection structures, the last type is hypercube system. So in a hypercube, a binary n-cube multiprocessor structure is loosely coupled system with n equal to 2 raised per n processors. So if I say it is a 1 cube multiprocessor, it means 2 raised per 1. It means it has 2 processors. So this is a 1 cube, and this is a 2 cube, so 2 raised by 2 is 4. Similarly, this is 8. So now we will see how it communicates from with each other. So if I want to go from 0 1 0 to 0 0 1, why it has chosen 0 0 0, we will see. So we use XOR gate. So let's say the source is 0 1 0 and the destination is 0 0 1. We will XOR both of them, and with XORing both of them, so XOR is 1 when the values are opposite. So 0 0 is 0, 1 0 is 1, 0 1 is 1. So the answer will be 0 1 1. So it can take the path from 010 to 001 through 000 or the 011. So one thing more to be noticed here is that in the two consecutive locations, only one bit is different than the other. So in this between 010 and 011, the LSB is the different bit, 010 and 000, the middle bit is the different one. So every consecutive locations have only one bit differing from each other, and to reach 001 we can reach through the 000. So XORing of source and destination has to be done, and then the particular path has to be taken. Interprocessor arbitration. The processors in a shared memory multiprocessor system request access to common resources through the system bus. If no other processor is currently using the bus, the requesting processor may be granted access immediately. The bus is shared here, and this bus can be used by a processor if no other processor is using it. So the arbitration must then be performed to resolve this multiple contention for the shared resources. So when there are shared resources, this contention has to be handled carefully, and it has to be done using different methods. So one of the method is serial arbitration procedure. So in this, PI is the P input, processor input, and PO is output. So this is the input part, this is the output part. Arbitration procedures service all requests on the basis of established priorities. A serial priority resolving technique can be established using a daisy chain connection of bus arbitration circuit. In this method, processors connected to the system bus are assigned priority according to their position along the priority control line. So what is happening is, so based on their priority line, one by one they are being served. The first one is having the highest priority, and the last one is having the lowest priority, and based on the priority everyone is given value 1. Which one needed it? The one who needed it will make PI as 1 and PO will be 0, because it will not pass the value. So it will take, let's say bus arbiter 2 needed the resource, so PI will be 1 for this part and PO will be 0 for this part, because it will not pass the value to the next bus arbiter, but because it has taken it. Let's say what will be the value of PI and PO if the control of the bus is given to that arbiter. So what will be the value of PI and PO if this current arbiter is given the control of the bus? So let's say this one needed the control. So what it will do is, this one will be given to PI here, and then PO will also pass this value as 1, but this one needs it, so it will not pass the value as value forward to the arbiter 3. So it will make PO equal to 0 and PI will be 1. So let's say arbiter 2 needed it, so PI will be 1 for arbiter 2 and PO will be 0 for arbiter 2. That's the only way it will not pass the value to arbiter 3 or arbiter 4. So this one will get, and our purpose will be solved. Parallel arbitration logic. So what is happening here is, there is acknowledgement and request. So whenever the request is being received, acknowledgement will be given by the decoder. How it will be given? So once the request is being given, the value is passed through the encoder. Encoder will encode the value based on some logic. This priority encoder will be generating 2 bits, which will be telling the decoder that 0001, or whichever the arbiter needs the bus line, whichever has the highest priority, it will be given. So let's say this priority encoder made the two values as 00. Let's say after receiving the request of all, and the highest priority was given to 00. So this 00 will be passed to this one. So this decoder will send the value to bus arbiter 1, and this one will be given the system bus. This is how the priority encoder and decoder will be helping to receive and acknowledge which bus needs to be given the resource. There are also some dynamic algorithms. The earlier we studied are all the static priority algorithms, but the dynamic ones are time slice, polling, LRU, FCFS, and rotating daisy chain. So if you are wondering what is LRU, LRU is least recently used method, and the FCFS is first come first serve. So let's see what are they. The dynamic bus arbitration algorithms. So the time slice means that a fixed length time slice of the bus time are offered to each processor sequentially in round robin fashion. So this time slice can also be thought of as a round robin, which you should have studied in operating systems. In what is happening in polling, bus grant signal is replaced by a set of lines called the poll lines, and which are connected to all the units. So these lines are used by the bus controller to define an address for each device. The controller sequences through the address in a prescribed manner. So the controller will be handling the addresses in some defined manner only, and whenever a processor that requires the access recognize its address, it activates the busy bus line. So whenever the processor whichever requires the maybe some address, that bus line will be busy and it will be given the access to the bus. After a number of bus cycles, the polling continues, and it continues to choose the next processor. So let's say there were some processors in sequence, and one by one polling was done. So it was this one was asked if it needed, it did not, if this did not need, it will pass the value to the next one. So if it needed, it will take, and it will not pass the value to the next one. So this connection will be lost, and for that particular request, this one has been served. So this is how the dynamic arbitration is done for the polling part. And for the LRU, in LRU what is happening is it gives the highest priority to the requesting device that has not been used in the longest period of time. So least recently used means the one who has not been served for a long time, it will be given the priority. For the FCFS, requests are served in order as they are received, so first come first serve. Is in rotating daisy chain, let's say these are the three processors, so the PO of the last one is connected to the PI of the first one. So this is how the value is being transferred. The interprocessor communication and synchronization. There are two types of processors, the tightly coupled or shared memory systems. In these, a portion of the memory is set aside which is accessible to all the processors, and this method is used for sending and receiving the messages. But in the loosely coupled systems, the messages are passed through message passing. There is no shared memory. All right. So when the memory is shared, the messages can be sent directly through the mailbox. It works as a mailbox. In the loosely coupled systems, no shared memory is there, and message passing is done for the communication. So for preventing the use of shared resources conflict, this conflict can be handled using three techniques: master slave configuration, separate operating system, and the distributed operating system. Let's see one by one. So master slave configuration, what is this? The one processor designated as the master executes the OS functions. The OS functions are only executable by one processor, which is the master, and for the slaves it do not perform any OS function. If a slave processor needs an OS service, it must request by interrupting the master. So master will be disturbed and it will be interrupted by the slave one, and slave one will be given the OS, and the function which the slave wants to perform, it will be performed after the current program has been completed. And for the separate operating system, so what is being done is any processor can execute the OS routines it needs. This organization is more suitable in loosely coupled systems, and where every processor has its own copy of the entire OS. So this is the most important part here. Every processor in the loosely coupled system has its own copy of entire OS. And for the distributed OS, it is the concept is around floating OS. So what is floating OS? Let's see. OS routines are distributed among the available processors. However, each particular OS function is assigned to only one processor at a time. This organization is referred as a floating operating system, since the routine floats from one processor to another. So the routine function which needs to be performed is being transferred from one processor to another within that operating system. So that is known as this floating operating system. Interprocessor synchronization. What we can see is, while communication refers to the exchange of data between the different processes, synchronization refers to the special case of the data where the data being communicated is control information. So synchronization is needed to enforce the correct sequence of processes, so the processes sequence is corrected, and ensure mutually exclusive access to the shared writable data. So synchronization is responsible for these things. So let's see, but what is binary semaphore? So in binary semaphore there are two terms: mutual exclusion and critical section. So in a multiprocessor system, it is crucial to ensure that data is not being changed by two processes simultaneously. This mechanism is called mutual exclusion. So when one process is being run, other process cannot modify the value of that system. So mutual exclusion must be provided to enable one processor to lock out access to the shared resource by other processor. So in the critical section, we can see that let's say this is a critical section, and once someone has entered in the critical section, no other processor can enter into the critical section, and this function will be completed. And if when this processor leaves this critical section, then only second processor can enter into the critical section. So at one time only one can perform. And a semaphore is a binary variable that is used to indicate whether or not the processor is executing its critical section. So semaphore, let's say S is my semaphore. If it is 0, it means it is not executing the critical section, and if it is 1, it means that it is executing the critical section. So that is why it has been written that it is a binary variable. So there are multiple techniques of doing the semaphore initialization. So one of the technique is test and set instructions in conjunction with the hardware lock. So it can be executed by TSL. So TSL is test and set while locked. It means that TSL SCM means when we are doing the test and set, it will be executed in the two memory cycles without interference as follows. So one during the test the memory location will be tested. So the memory location, let's say this was my memory location. At this memory location some value is being written, let's say it is 1. So this one will be sent to the R. So R is the register, processor register. So at the whatever was at this memory location, it will be sent to R. Even if it was 0, this one will be given. If this test had a negative response, so it is negative. If it is 0, it is positive. If it is 1, so even if it was 0, we would set it by sending the value to this MSEM. So this is the memory location at SCM semaphore's location. Alright, so if it was 0, let's say, then it would be replaced by this 1 using this set semaphore method. Thank you.